So this one is x plus h, a number whose nth root then nth power is itself. X and X are cancelled. H and H are also cancelled. So this is 1. And the denominator, if X is a non-zero number, when n is an odd integer, or x is a positive number when n is an even number, we have by the continuity of the nth root function. By letting h be 0, this is 1, this is x plus 0, nth root, n minus 1 power, x plus 0, nth root, n minus 2th power times nth root of x. So by the continuity of the root function. Okay, here, if n is greater than 1, they are exactly n terms here. N minus 1, the first term, the second term, nth term. So they are n terms of the same number. Okay, if we express this in terms of exponents, finally, use laws of exponents 1 over n x minus we have minus and minus is plus, and the n are cancelled, minus 1. So again, we have when the exponent is a unit fraction, the differentiation rule is again by letting the coefficient be the original exponent. And the power of x is 1 decrease this by 1. Of course, here we have some condition here. X is not 0. Because if x is 0, then denominator is 0. So we cannot use this way. We cannot use this function. Okay, this means this one. So here we can, as you can see, if x equals 0, we have to treat this separately. And when n is an even number, we assume x is positive. Because if n is even, inside this root cannot be a negative number. Okay. So all differentiation formulas are just under very mild conditions, very gentle conditions. Almost valid, almost true. When the numbers or the expression in this formula, if they exist, then the formula will be true. Okay. So for x is non-zero, we have this differentiation formula. Okay? Can I erase this? Sometimes some teachers just omit the derivation because it takes time. Take some time. Okay. If n is greater than 1, then if x is non-zero, then its derivative exists at any positive number. For example, here, the tangent. Here has a tangent. When x goes to 0, the slope of the tangent goes to here is 0, positive 1, so goes to infinity. Goes to infinity. Approach to a vertical tangent. Okay, this is an odd number. If x is not 0, here or here. The tangent exists and not vertical. Therefore, we have this formula. This is even, no wonder. The slope here and here are the same. When x approaches 0, then this one goes to 0, and this is constant 1, so the slope goes to infinity. Means this curve has a vertical tangent here. Vertical tangent here. Okay, at the origin has a vertical tangent line. There is a tangent line to this curve at this point. Okay, finally, at the zero. How about at zero? At zero, we have to check separately. For convenience sake, let's consider this quotient limit when h approaches 0 from the right. That is, I want to consider this is the slope of the secant line. This is h, this is 0. For this case, or for an odd number case, then h goes to 0. Okay, this is the square root of h. This is 0. This is h raised to the 1/n power. H raised to the 1 minus 1/n power. Okay, so this is a positive number. And when h approaches 0, this is also approaches 0 from the right. Because h is positive, this number is always defined. 1. A positive constant approaches 0. So this limit does not exist and is infinity. An infinite limit here. So as you can see at the origin, the slope does not exist. In fact, for n is an odd number, there is a vertical tangent here. For n is an even number, because this is not smooth, not continuous at 0. So this function is not differentiable at 0. We have a theorem. Differentiability implies continuity. Right? Differentiability implies continuity. If x is differentiable at some number, then this function is continuous at this number. Differentiability is stronger than the continuity. Stronger. Okay. And the continuity is stronger than the existence of the limit. So everything seems very simple. But gradually, if you not study hard, you will find everything is very unfamiliar. Okay, so we already solved this problem. And we know the reason that this function is not differentiable at the origin, not because of this expression and this expression are equivalent, same. You cannot say, because when x equals 0, the denominator is 0, so this function is not differentiable at 0. Wrong. Because we have derived this formula, already assume x is not 0. Okay, you cannot use, the hypothesis here is x is not 0. So you cannot say, oh, so at 0, it is not differentiable. You have to discuss the 0 separately. Okay, because of this, the function f of x